Okay, good morning. So let us start the new lesson. So, yeah, we want to talk about a new concept in complex numbers, and that is the very simple concept of the modulus or absolute value of the any complex number. So if you have a complex number, then the absolute value or called modulus of the complex number z is denoted by the same symbol that you use for real numbers, but it is defined in this way. So it becomes a square root of the real part to the 2 plus the imaginary part to the 2. Okay, and then take square root sign of that. So what the number you get is a non-negative number. That non-negative number is called the absolute value of your complex number. And then, I don't know, might be you have read the last sentence, but what is geometric meaning of absolute value? The distance from the point in the complex plane to the origin, yes? So if you want to understand this, so let me, for example, draw this coordinate system. So, for example, let us say that this point z is somewhere here. Okay, do you remember we talked that this can be represented by an arrow here as well, or a vector. So you can say that, okay, the length of this vector, or in other words, the distance from the point to the origin, is what we call absolute value. So if I put a point here, absolute value of z geometrically means the length of the vector OA, or I don't know, you can say the distance from O to A, yes? So sometimes you write it in this way. So it is very important. So if you have a number which is farther away from the origin than the other number, its absolute value is greater than the other one. So that's a measure of closeness, and I don't know, farness is wrong. What is the correct word? Okay, anyway, the distance probably, the distance for the origin. Okay, so that's a very simple concept. Let me just be careful and just solve some very simple examples. I have given you some, complex numbers, and I'm asking to calculate the modulus of each of these complex numbers, yes? So what we can do for number 1, we can just write z, absolute value of z is equal to the square root of 3 to the 2 plus minus 4 to the 2, which becomes square root of 9 plus 16, square root of 25, and the answer is always 5. Do not write plus or minus, okay? Okay, so what is the absolute value of the second one? So number 2. So you can immediately answer, what is the absolute value?
Square root of 2.
No, I, yes? It's 1, yes? Because where is I? I is, so you can imagine that, where is I? If I ask you locate I in the complex plane, you go 1 unit up on the imaginary axis, this is I. And if I ask you what is the distance of this point to the origin, it's clear it's 1 unit, yes? This is from geometrical point of view. But algebraically, how you calculate that, you would say that when you say z is equal to I can be interpreted as 0 plus 1 times I. So what you say is that absolute value of z is a square root of 0 to the 2 plus 1 to the 2, which becomes square root of 1, which of course is 1. So it is better to understand it geometrically as well. It's extremely important, okay? So what is, for example, number 3? What is the absolute value of number 3?
3.
It's 3, because minus 3 I is 1, 2, 3. It's minus 3i, and if I ask you what's the distance, you would say it's positive 3, yes? So, and if you calculate it, so z can be written as 0 plus minus 3i, and then if I ask you calculate absolute value of z, so it becomes square root of 0 to the 2 minus 3 to the 2, so it becomes square root of 9, which is 3. And now, can you tell me what's absolute value of 4? Yeah, it should be 4, otherwise we would be in trouble, yes? Because I told you that we want to keep the arithmetic the same. So if I ask you what is the absolute value of 4 before studying complex numbers, you definitely would answer 4. If I want to come up with a different answer, then I would be in trouble, yes? So this is good that you get the same answer, but do we really get the same answer from algebraic point of view as well? The answer is yes, because if I want to write this, how should I write it? I would write z is 4 plus 0 times I. So this means that absolute value of z is equal to square root of 16. 16 plus 0, which is 4. Okay, and what is absolute value of minus 5? 5. And let us calculate the absolute value of this one. So what can I do? Number 6. What is absolute value of z? It is just simply square root of the first one to the 2 plus the imaginary part to the 2. But what is the first one? It becomes 3/4, and then the other one is 1/4. So it becomes square root of 1, which is 1. Yes? So it means that this point lies somewhere on the unit circle. Yes? Because its distance to the origin is 1 unit. So it lies on the unit circle, but in which quadrant? Because the real part is negative, the imaginary part is negative. So it lies in the third quadrant. In the third quadrant on the unit circle. Okay. These properties, I have mentioned them as a theorem here. These are actually spread around in the book itself as exercises. For example, this one is a level 3 question in the book. Show this is true. Okay. I want you, if you want to study in the future, it's very important to know these things by heart. These are the properties of the absolute values. Some of them are actually easy to realize, but in principle, if you want to give me a proof, you need to prove it rigorously using algebra and definition. Yes? So do you think that the first one is clear? Absolute value of z conjugate should be equal to the absolute value of z. Because do you remember what was when we conjugate, what happens? We flip into this real axis. And this doesn't affect the distance to the origin. Yes. So for example, if I have this, if this is my z, where is z bar? Z bar is just the flipped one here. Okay. And it is clear if the distance from here is, for example, 2, the distance from here to here remains 2 because of this symmetry. Yes. So geometrically, it is very clear that these two should match. But even algebraically, it is clear, yes, because what is z bar? Z bar is x minus yi. And if I ask you what is absolute value of z bar, you would say it becomes square root of the first one to the 2 plus the second one to the 2. But it becomes exactly x squared plus y squared, which is exactly equal to the absolute value of z. So this is from algebraic point of view, yes? But so I think it's always good to have both pictures in head, okay? And a very simple but very nice formula is this relation. So if you multiply a complex number by its conjugate, it becomes the absolute value of the number squared. Yes. So I don't know if I I have repeated it here. Okay, so I can just go here and write the proofs. So number 2. So let us consider this as an exercise. So how should I do that? I will start from the right hand side. I would say, let me write it like this, if I want to be clear. So I would say let z be equal to x plus yi. Okay, then z bar would be x minus yi, and the left hand side is equal to the right is equal to zz bar. The right hand side, sorry, is equal to zz bar. It is equal to x plus yi multiplied by x minus yi. And hopefully you realize this is a conjugate pattern, so it becomes the first one to the 2 minus the second one to the 2. So this becomes x squared plus minus y squared I squared, but I squared is nothing except minus 1, so it becomes x squared plus y squared. If you want, you can write it in this form, yes? Then to power 2. But if I ask you what is the expression in the pair of brackets, that is nothing except absolute value z, and then I have a power of 2 here, so it becomes absolute value of z squared, and that is equal to the left hand side. Yes, so that is a very nice and compact formula, and we will see some applications. Hopefully I have given some examples of that. Okay, another extremely important one is the geometric interpretation of the absolute value of the difference of two complex numbers. Okay, so the absolute value of the difference of two complex numbers gives you the distance between these 2 points on the complex plane. Okay, so that is extremely important to understand. So if I just ask you absolute value z, you can interpret it in this way, and then this gives you the distance from z to the origin. Okay, but in general, if I have two non-zero complex numbers, if I subtract them and take the absolute value, it gives you the length of the, so let me write it in this. It will give you the distance between these 2 points on the complex plane. But why is that true? Yes?
Because when you expand it, it becomes the distance formula.
It becomes a distance formula, exactly. So if I want, for example, to prove number 3, so it's very important, by the way, at least try to remember this one. Okay, so here, if I want to prove it number 3, I would say that let z is already given, so let me assume that, let me write it in this way. Let z be equal to x1 plus y1i, and w be equal to x2 plus y2i. Now, if I ask then what happens for z minus w becomes x1 minus x2, yes, plus y1 minus y2 times I, yes? And now this is a new complex number. I am asking you to calculate the absolute value of this complex number. So the formula tells you that you need to take a square root of what? Of the real part squared plus the imaginary part squared. But I hope that you remember this is exactly what you learned in Math 2C as the distance formula. And that is the distance between a point with coordinates x1 and y1, which is this point, and the point with coordinates x2 and y2, which is that point. Yes, so I just explain it orally. Yeah. Is that clear? Okay, but this one is a level 3 problem. This is not in the book, but this is also clear. You can prove it yourself. So this is very nice to understand what is the meaning. It tells you that if you multiply two complex numbers and then calculate the distance of the new point to the origin, it becomes equal. It is very interesting. It's not geometrically clear. The reason it's not very geometrically clear because if I give you z and w on the complex plane, there is no very straightforward way to imagine where zw end. So when the zw will be. Yes, if I give you just two complex numbers randomly, okay, so you can find a point for each one of them. And then if I ask you multiply them, it becomes another complex number. There is no geometric operation that you, by looking at these 2 points, understand where we will end up when we multiply. So this is why it's not geometrically very clear that this should work. It means that if you multiply and then find the distance of the multiplication to the origin, it becomes equal, strangely, it becomes equal if you calculate the distances first and multiply the distances. Yes, it's not that trivial geometrically. But algebraically, it happens to be the case. And by the way, we should expect something like this because I told you that I want to keep the arithmetic the same. Yes? So we had this formula for numbers, for real numbers, if you remember. If A and B are real numbers, we have this formula that this should be correct. So this we should expect that might happen. Yes? But we need now to prove it. So how can I prove it? Again, the same story. So I just take two of them. So this part that I am writing, I don't know, you can check it in the book. This is one level 3 problem in the book. So number 4. I would say the same thing. So let us take z to be this one and w to be this one. And I move it here. So I don't want to write the sentence again. So what I do, let us multiply z by w first. What happens? It becomes x1 plus y1i y1i multiplied by x2 plus y2i. If you multiply them, it becomes what? x1 x2 plus x1 y2i plus x2 y1i, and then finally minus y1 y2. Yes, because I squared is minus 1. And if I want to collect them in the standard form, it becomes x1 x2 minus y1 y2 is the real part, and then I factor an I out between the other group, so it becomes x1 y2 plus x2 y1 and I. Now I ask you, what is the absolute value of this product? You see, it's a fairly complicated operation when you multiply them, yes? So what happens, you would say that this becomes equal to square root of the real part to the 2, x1, x2 minus y1, y2 squared, plus the imaginary part to the 2, x1, y2 plus x2, y1 to the 2. So do you have any suggestions? What should I do now? I want to somehow connect this strange number, a little bit strange number, to the absolute value of each one of them individually. Yeah, this is probably the most natural thing that we can do. And if you can look a little bit ahead of you, you see that a very bad term will be cancelled out. Yes, this cross term will be cancelled out. Why? Because it becomes the first one to the 2. X1 to the x1, x2 to the 2. So this becomes this one to power 2, this one to power 2, minus 2 times the first one times the second one. Yes, and plus the second one to the 2. And then the next one becomes x1 to the 2, y2 to the 2. And then 2 times the first one times the second one. And then plus the second one to the 2. Yes. Yeah, so let me see if I have enough space. Yeah, I cannot do much better here, but let us move it here. Okay, is that understandable? I'm just expanding them. But can you see one term is crossed over, yes? Yeah, they are exactly the same in a different order. x1, x2, y1, y2, minus 2. x1, x2, y1, y2, positive 2. So they are exactly the same, so I can cancel them out. So this one and that one is gone. And then what can I do? Yes? Collect the terms. Can you see which one with which one?
x1 squared, x2 squared, with the other x1 squared.
Yeah, exactly. And I take x1 squared out. Yes, so I will take this one with that one. I factor x1 squared out. And then I will take this one with that one. And what was that y? I was careless when that is y1. So it is not working in that way, is it? If I take this one, yes, that's y1. Yes, you see, this was y1, but when I was writing it, I didn't write this one, so that is y1. Yes, that's quite good. So what I do, I will take this square root sign, and then what I do here, I factor x1 squared from that group. It becomes x2 squared plus y2 squared. And from the other group, I can factor a y1 squared out. From the last one, x2 squared, and from this one, y2 squared are left. Agree? That I just factored them out. And the good point that you immediately realize that another common factor emerges. So I can pull it out again. Yes? So that's the factorization. So this becomes square root of x to the 2 plus y to the 2, I pulled it out, and then it becomes x1 to the 2 plus y1 to the 2. But I hope that you agree with me that I can write it as in this form, x1 to the 2, y1 to the 2, multiplied by this one, yes? x2 to the 2 plus y2 to the 2, yes? Because these are real numbers. Now, if I ask you what is this one, this is exactly what we call absolute value z, and what is this one? This is exactly what we call absolute value of w, yes? So this becomes absolute value z times absolute value of w, and we are done. Okay? I recommend you to do this one yourself at home. So even though this is not in the book, but at least you need to know that this is also very strange. If you divide two complex numbers, the distance of the quotient to the origin is equal to the quotient of the distances to the origin, which is not trivial, okay, as in geometric level. Any questions here? No? Okay. And now there are some points that I want to mention here. For every complex number z and every integer n, you also have this one. You can use mathematical induction, for example, to prove it for natural numbers. And then you can also use some kind of mathematical induction for negative integers. But it should be trivial because, for example, if I ask you what is the absolute value of z to power 3, you would say this means absolute value of z times z times z. This is the meaning of z3, yes? And we just learned that we can write it as absolute value of z, absolute value of z, absolute value of z. So this becomes absolute value of z to power 3. So it doesn't matter if you raise to power 3 first and then take the absolute value, or you take the absolute value first and raise it to power 3. Yes, but which one is easier for us to do? Which one is easier? Yes? The second one, yes? Because here, if you want to raise to power 3 first, you have a complex number containing the real part in general and an imaginary part. And if you want to raise it to power 3, you need to use binomial theorem to raise it to power 3, simplify it, and then it becomes a complex number, and then take the square root. Sorry, take the absolute value. But here, you have just one single complex number, you take the absolute value, it becomes a number. And then what you do, you just raise a single number to power 3. Even though they are equivalent, the answers are the same, but the second one is much easier for us to do it. And another point is that I want to make sure that you understand that because this formula was correct for the product and division, it doesn't necessarily mean that this is also correct for addition and subtraction, which is not the case. Yes, absolute value of z plus w might be sometimes equals to this, sometimes, but in general it is less than or equal to this. So there is no guarantee that absolute value of the sum becomes equal to the absolute value of the first one plus the absolute value of the second one. It's still interesting because addition is more easier operation, but this formula doesn't work for addition. It works for a more complicated operation as multiplication and division. Okay, and this is called the triangle inequality. Why is that? You can imagine it something like this. If I give you, I will write and clean here. So for example, if you have 2 points, so if this is your z, I told you that this can be written in the form of a vector, can be represented as a vector, and then if I say what is w, you can represent it by w, by this vector. And then it turns out that you can convince yourself, if I ask you represent z plus w, it is very nice. It enjoys the same property as vector addition. So and that is not very hard to see, yes, because when you add two complex numbers, what is happening? You are adding the real parts separately and you are adding the imaginary parts separately. So it's exactly like we do for vectors. I don't know if you remember vectors from Math 1C. If I give you 2 vectors, you know that every vector has 2 components. And if you want to add the vectors, you can add the components. And that's exactly the same scenario. So if I ask you geometrically, can you tell me what is z plus w? You would say yes. This is the vector z plus w. And then it becomes geometrically clear, yes? The length of this is always smaller than the length of this plus the length of that in any triangle. The length of this is the length of w. The length of this and the length of z are the same. So it means that if I ask you what is this length, you would say this is the length of z. If I ask you what is this length, you would say it's the length of w. Now you know that from this triangle inequality that if I add 2 sides of a triangle, it is always greater than the third side. So this is why we have this inequality. But of course, in real triangles, we will never have equality. Yes, if you have a real triangle, unless you have a degenerate triangle. Yes, that degenerate triangle gives rise to sometimes this possibility. Yes, and that happens if I have a vector here. The second vector exactly lies on the same vector. If I add them, the vector becomes this. And then in that case, I have equality sign. But if this case does not happen, I have always strictly smaller than this. Yes? Is that clear? So make sure that you don't confuse that formula for product and the quotient was correct, but not for addition or subtraction. Okay, so let us solve a little bit more advanced problem here. So for every complex number z and w, show this is indeed the case. Z plus w squared is equal to that. So I would prefer to pause the video to see that how you can solve the problem yourself first, okay? So one way to solve this problem is probably a direct approach, yes, as we have done so far. So you can take something for z, something for w, calculate the left-hand side, calculate the right-hand side, and then compare them, yes? This is probably an approach that, of course, works, but I want you to solve it through theorems. It's a little bit more advanced way of solving this problem, and it would be shorter, okay? So if you have started with just taking that, okay, let us take z to be x1 plus y1 and then w, something like that, that's okay, it works, but I want to use the theorems as much as possible. Okay, so for example, the first thing that I want to use is this theorem. If you are interested in the absolute value of a complex number to power 2, you can write it as that complex number multiplied by its conjugate. Yes, this is something we just learned today, yes? And we had also some other formulas, yes? Do you remember what can I write for this combination?
Z bar.
Z bar plus W bar, so we learned about that. And then can you tell me what we learned about this?
The real part.
2 times the real part of Z, yes? So we already learned about these theorems, so I can use them if I want to. Okay, so this is a better way, more elegant way to solve the problem. So I would say that I will start from the left-hand side. So the left-hand side is absolute value of a complex number to the power of 2. So according to this theorem, I can write it as the number itself multiplied by its conjugate. Yes, is that understandable? That's the same theorem. But now another theorem tells me that z plus w, instead of z plus w bar, based on my previous previous theorem, I can write it in this form. Yes? And then because the arithmetic is the same, I can distribute it. I can write z times z bar plus z times w bar plus w times z bar plus w times w bar. Yes? Okay, but can you write something for z bar? Absolute value of z squared, which is good to have. The last term is absolute value of w squared. Yes? Now I just want to, you see, at least 2 of them appeared very shortly, immediately. So then I want to see that what you say about the rest. I have this combination. Let me write it down. Okay, let me ask you, what can I write for this? What can I write for this part now? Apparently, it is clear what it should be, yes? Because this is already this part. This is already this part. And if this is going to be true, yes, we are supposed to show that this is true. It means that somehow this will be this. Yes, but can you say why? Okay, let me write it in this way. Instead of z w bar, I keep it. But do you agree with me if I write it in this form? For the second one, do you agree if I write it in this form? Yes, because if I ask you what this is, let me write with a different color here. So if I ask you what z w bar is, you write it as z bar times w bar, yes? But do you remember what was w bar? It was just w. So it becomes z bar w. So now you agree with me, hopefully, that z bar w, which is this one, can also be rewritten in this form. Yes? And now what's happening? This is a number, let me call it capital Z. This is the same number, capital Z, but I have a bar on it. Yes? So it becomes Z plus Z bar. According to what you said, it is 2 real parts of capital Z. Yes? But capital Z, what was that? It was ZW bar, and we are done. Yes? So this becomes equal to Z to the squared, this one squared, and then 2 real part of Z W bar, and this is exactly equal to the right hand side. Yes, is that understandable? So this is a better way. So you see, I'm using a lot of theorems one after the other. Otherwise, you can always use algebra. You say that z and w are these numbers. I calculate the left-hand side, simplify, calculate the right-hand side, and simplify, and compare them. That's also completely true. But it's better to learn to do these things. Now let me ask you one question to test your understanding here. If I have two complex numbers in the complex plane, each one of them can be represented by a vector. Yes? Is that clear? Can you, based on this exercise, say that when these two vectors are perpendicular? So z and w are two complex numbers. You specify them in the complex plane, connect them to the origin, it gives you two arrows. These arrows might be perpendicular or might not be perpendicular. Okay, can you see based on this one, what is a necessary and sufficient condition for those two vectors to be perpendicular? You need to think about this part. This reminds you of a very famous theorem, yes? What's that theorem? Pythagoras theorem. And Pythagoras relates itself to perpendicularity of the sides, yes? So now can you see what happens? Yes?
If two real numbers and bar w is 0.
Is 0. So if this part is 0, it means that, so if this is z, yes, and this is w, so you know that what is z plus w? Z plus w is the third side of the triangle, yes? So now this gives me the length of this one to power 2, this gives me the length of this one to power 2, this one to power 2. If this is equal to that, it means that I have a right angle triangle. And in that case, this will go away and this will be left. So it means that a necessary and sufficient condition for two non-zero vectors in complex plane to be perpendicular is that this combination is 0. So that's, or otherwise you can say ZW is pure imaginary. If ZW bar is pure imaginary, it means that the vectors Z and W are perpendicular to each other. Okay, so that's one application. But these type of examples are in the book. And they are very, very important to understand. There are two ways to solve these problems, algebraically, geometrically. Geometrically is usually hard. Algebraically always works. So you just need to manipulate algebraic expressions. But I really want you to understand, if possible. Sometimes you do not have enough knowledge of geometry available to be able to discuss it geometrically. And if the problem is extremely hard, no one can actually guess it. But can you, for example, tell me, if I represent this equation, what do I mean by the way? So this is an equality. There are some complex numbers that satisfy this condition. Some of them does not satisfy. I am thinking about all of them that satisfy this condition. I want to highlight them one by one. And my point is that when I look at the final picture at the end, is there something that I can say? Yes, Emil?
It should be a circle with radius 3. What origin?
Not origin. Radius, so circle is correct, radius is correct, but the center is not the origin. Yes, Alex?
The center should be 2, 0.
2 and 0. Yes, because do you remember what I told you? What is the geometric interpretation of this? It is the distance between these two complex numbers in the complex plane. So how should I interpret this? So number one, if I want to understand it, I would say that absolute value of z minus 2 equals to 3. It means that absolute value of z, 2 is this complex number, 2 plus 0i. Do you agree? This is another way of writing 2, so 3. So this is plane of your w here. So it means that the distance from this point to w should be constantly equal to 3. So it means that the center of the circle is this point, which is 2 and 0. So that's not the origin. So it means that yes, in principle, if I understood it correctly, the picture that I will get is a circle centered at 2 and 0, so centered at here. Yeah, of course it is very hard to draw the picture, and the radius is 3, so it should pass from here, from here, and here. Yes, so if I can draw it more or less correctly, so this would be what you should expect to get. Yes, I don't know if it works or not, but anyway, yeah, something like it worked actually very good, except this one. Anyway, you understand that should be a circle, yes, with the center this. And of course, this is a bad feature. You might get a feeling that I am also. Now, let us get rid of this because that's not a good impression. So I don't. So this is just a circle. So let me make it filled, and try not to use the feature. Yes, hopefully like that. So that is just the rim of the circle. By the way, when you say circle, it exactly means that curve. Yes. So this is that one. This is from geometrical point of view. So sometimes it is important to realize what is the geometry behind an equation. If I want to solve it algebraically, how should I solve it? So I would say that let z is x plus yi, and then I put it in this equation to see what happens. So what happens? It becomes x plus yi minus 2, absolute value is equal to 3. So this means that I can write it as x minus 2 plus yi is equal to 3. But if I ask you what is the absolute value of this number, you would say square root of the real part to the 2 plus the imaginary part to the 2 is equal to 3. If I raise it to power 2, it becomes x minus 2 to power 2 plus y2 is equal to 9. I don't know if you remember your lesson from Math 3C. This is the equation of a circle. So if you have forgotten, let me write it here. X minus alpha squared plus y minus beta squared equals to r squared. This is the equation of an equation of a circle, of the circle, with the center alpha and beta and the radius r. Okay, so this is what you'll studied in Math 3C if you remember more or less. So if you compare this one and this one, you immediately see that alpha is 2, beta is 0, and r is 3. Yes, so that is exactly what we predicted. Okay, what do you predict for this one now? This is not equality, this is inequality. So you need to interpret any absolute value as a distance of points. So how do you interpret this, and then what would be the answer at the end? What is this? I mean, can you just imagine the region or the curve or whatever that is described by this inequality? Of course, if you cannot, you can solve it algebraically, but even algebraically, if you have forgotten the equations of circles and things like that, you will be in trouble. Yes?
Would that be a circle at minus, like 0, minus 2, but all the contents inside is
Exactly, yes.
counted.
But what is the radius?
The radius is 2 inclusive.
Yes, that's correct. Yes. So what does it mean? Because you need to, because when you want to interpret the absolute value of it as a distance, this sign should be negative. But this sign is positive here, but that's no problem. Yes. What can I write? I would say that z plus 2i less than or equal to 2 can be interpreted in this way: z minus 2i. Yes. And minus 2i can be written as this one. Yes. Yeah, it seems a little bit strange, but it's not hard. First of all, 0 doesn't have any role. Minus becomes positive 2i. So what you see here is exactly what is here. So I am not changing anything at all. But what is the point? The point is that this sign is now negative. So this absolute value can be interpreted as the distance of this point to this point. And I am interested in all those points whose distance from this point is either equal to 2 or less than 2. So it is clear, yes? If I only care about equal to 2, then it becomes a circle with this center and radius 2. But now I am also interested on the points, in the points that are actually the distance from this are smaller than 2. So it means as what Alex said is completely correct. So what should I write? The first thing that I want to imagine, I will draw this, for example. So where is this point? 0 and minus 2i. So here is minus 0 and minus 2i. So this point is 0 and minus 2i. And then I want to have the distance of points from this point equal to 2 or less than 2. So if I want to try to draw it more or less something reasonably good, so this would be this circle. But everything inside, so might be if I can use this trick, this will be good actually here. So let us see if it works this time. Yeah, good. So that is exactly what we want to do, yes? So this is this circle and this one. If it was strictly less than 2, you need to show me that you draw this part in this dashed form. Yes, it means that you are excluding that. But here you have to include that. Yes? Might be the hard part is number 3. Before calculating here anything algebraically, can you guess what would be the shape? What would be the region? Even if you cannot, you can interpret it for me. So how do you interpret it geometrically, yes?
Is it the intersection between two circles?
No. Because the left-hand side is not a circle, because on the right-hand side you have another expression. An expression like this equal to a number represents a circle. So this is equality not between two equations of two circles. So can you just tell me what is the interpretation of this? So it is the distance of some points from the points 0, 3 and 0. And this is the distance from the points z to another point 1 plus 2i. Do you agree? Because I can write it in this form. Okay? So it means that I have two fixed points. One point is 3, another point is 1 plus 2i. These are two fixed points on the complex plane. And I am interested in those points that the distance of those points from this is equal of the distance of the same points from the other point. So you need to imagine this in your head so that you can come up with a conclusion. Let us forget about this. Let me just ask you here. I give you a fixed point here, another fixed point here. Okay? And I ask you to give me the loci. This is the word. The loci, it means the geometric positions. Give me the loci of all points that are equidistant from the point A and B. It's not hard to imagine it in this way. What is this? Yes? No, what is the loci? What are those points? I'm not asking I'm not working in coordinate system. I give you 2 points, one here, one there, and then you want to find, it's in the space it is different. But on the plane, I give you a point here, another point here. And I am asking you find all the points here so that the distance from those points from here and there, they are the same. Yes, there is a name for that line. Do you know that? So can you tell me how should I find that line? You probably will say that I will connect this thing and then find the middle point and then? No, vertical, perpendicular, yes? This is called perpendicular bisector. It is perpendicular to the line segment and it divides it in 2 halves. The name of this line is called perpendicular bisector of the line segment AB. So that is important to understand. If I give you 2 points in the plane and I ask you for all the points in the plane that have the same distances from these two, the answer is the perpendicular bisector of the line segment. Yes? So if you understand that one, then you can immediately answer this question. So if I want to answer number 3, what should I do? I would say that I will locate these 2 points. What are the points? So let me first interpret it in this way. I would write it as z minus 1 plus 2i because I want to have the minus sign in between. And then on the other side, I would write z, I can imagine it as 3 plus 0i, yes? So this is the way that I imagine this formula in my head. And then I will go and find these 2 points on the complex plane. So what should I do? So it means that one of the points is 3 and 0. So yeah, I was a little bit careless. Let me draw it from here. So 0 and 3 and 0. So this is 1 point here, 3. And the other point is 1 plus 2i. 1 plus 2i is here. Yes, it's 1 plus 2i. So it means that if I want to understand this, I need to connect these 2 points together and then draw the perpendicular bisector. Yes? If I do that, I will get this one. Yeah, so more or less this. So this pinkish line is actually the line that I am looking for. By the way, you see that this formula was more complicated than the previous one, but the shape was simpler. It was just a simple line, yes? But now, can you tell me what's the equation of this line? You are in the technique 3rd year, yes? So you should be able to say, what's the equation of this pinkish line? What is the slope of this pinkish line? Yes?
It's 1.
The slope is 1. Agree? Everybody understand that, yes? Because if I go 1 unit to the right, it go 1 unit up. So the delta y over delta x is 1 over 1, which is 1. So the k value is 1. What is the m value?
-1.
If my picture is correct, it's -1. So the equation that you predict is y equals to x minus 1. Yes? But now let us solve the problem algebraically. If it is, because sometimes it is hard. For example, if I just put a 2 here, then it's not easy to guess this. So if I give you the same thing on the left, but I give you a 2 here, okay? Can you predict what will happen? So this is a very ancient problem that is called Apollonius circle. So again, it turns out to be a circle, but not with the center that you can predict immediately. Okay, so if you want, you can solve the problem. In principle, you should be able to do it algebraically. It's hard for you to do it geometrically because you don't know that theorem, probably Apollonius, theorem. But algebraically, you should be able to solve it and predict it is a circle. Just do it at home. If you want, if you are interested, write it as a home assignment for yourself and do it at home. But let us now do this algebraically. How should I solve the problem algebraically? So let me add one more page here. Where I am here now? Yes. Yeah, let me just get rid of this. And then let me open this one. Okay, so if I want to solve it algebraically, how should I say that? This was the equation, yes? Z was minus 1 plus 2i is equal to z minus 2. Am I right? Yes? No, 3. It was 3. Okay, so what should I do now? It is z minus 3. So if I want to solve it algebraically, I will say that z is equal to y plus x plus yi. I put it here. So it becomes x plus yi minus 1 plus 2i. And then I will take the absolute value is equal to z is x plus yi minus 3. So if I simplify these expressions, what happens? On the left-hand side, I will have x minus 1. And then I will have y minus 2i. And then absolute value. On the right-hand side, I will have just x minus 3. and then plus yi absolute value. Yes, algebraically. But if I ask you what can I write for this, what can I write? It becomes a square root of the first one to the 2 plus the second one to the 2. On the right hand side I can do the same thing. The first one, the real part to the 2 plus the imaginary part to the 2. And then I square it to get rid of square root signs, and then I expand them. So what happens? It becomes x squared minus 2x plus 1 plus y squared minus 4y plus 4. On the right hand side, x squared minus 6x plus 9 plus y squared. Yes? And now interestingly, you see that x squared and x squared are cancelled. So let me just do them. X squared and x squared are gone. Y squared and y squared are also gone. So if I simplify things a little bit, I can keep y on the left, and I can move every x's to the right. Yes? So what happens? I will have minus 4y is equal to minus 6x plus 9 plus 2x minus 1 minus 4. So minus 4y is equal to minus 4x. And then what is the number? Plus 4. And if I divide by minus 4, it becomes x minus 1 as we predicted. Yes? So in algebraic way of calculation, you don't need to have any intuition. So this doesn't teach you that much if you are interested to understand deeper things, yes? But if you try to motivate yourself first and then try to check it algebraically, that would be great. But of course, sometimes it is not easy. So this is why somehow algebra is a little bit superior to geometry sometimes, yes? Any questions? No? No, because in that way, yes, you can check your answer, but you have already come up with the answer.
I mean, because we did a graphical first, like on a test, if we made a graph.
No, on a test, you need to decide if you want to do it geometrically, if you want to do it algebraically.
Yeah.
But you can convince yourself what I did geometrically is correct algebraically or vice versa. Yeah. But anyway, that's up to you. So I just want you to understand the geometry, because understanding the geometry of complex plane is important, even though most of the time you can do this algebraically. Yes? Is that clear? Okay, I would stop here. So if you want, you can practice yourself. Any questions? Any particular questions here? No? Okay, so thank you. Let me just stop this.